space has a way of lying to us. Scientists call Proxima Centauri a neighbor. But neighbors are close. That faint red dot of light is 4.24 light-years away, a distance so vast that even a beam of light, racing faster than anything we could ever build, needs more than 4 years just to get there. It is the nearest star beyond our sun, and yet it sits across a gulf so enormous it may as well be infinity. To reach it is not an adventure. It is a gamble against physics, time, and human fragility. Every kilometer forward becomes a reminder that the universe is not built for visitors. It is built to keep its distances intact. So why does humanity keep chasing that red dwarf? And what would we sacrifice if we tried? If you enjoy thought-provoking stories like this, please like and subscribe and tell us where in the world you are listening from. Let's begin. When astronomers say Proxima Centauri is our closest star, they frame it as a friendly neighbor. But neighbors are people you can walk to. In space, even nearby, objects sit across deserts of nothingness where distance loses meaning and human intuition collapses. The human mind does not understand cosmic distance. It pretends to. We picture lines on a star map or glowing dots on a dark background, and we think proximity works like it does on Earth. A road between cities, a flight between continents. But the scale of interstellar space is not a bigger version of what we know. It is a completely different environment. Between stars there are no highways, no convenient stepping stones, only an endless black ocean where the concept of close becomes absurd. The gap between the Sun and Proxima Centauri is so large that if a spacecraft traveled as fast as a commercial airliner, it would not arrive in centuries or even millennia. It would take longer than human civilization has existed. Even light, the fastest thing the universe will ever allow, moves at a pace that feels sluggish at this scale. Light from Proxima takes more than 4 years to reach us. That means every time you see the star, whether through a telescope or on a scientific graph, you are not seeing what it is. Proxima could have gone silent yesterday, flared violently, or swallowed its own planets, and we wouldn't know for almost half a decade. It is historical. Try converting the numbers into something familiar. Imagine shrinking the Milky Way until the sun becomes a single grain of sand resting on the palm of your hand. On this scale, Proxima Centauri, our comforting neighbor, would be another grain of sand, sitting several meters away across a barren stretch of floor. Nothing in between. No stars, no planets, just empty space. That is how the galaxy works. A glittering swarm of stars suspended in an ocean of darkness so deep and so quiet that most of it will remain untouched forever. And Proxima is the nearest one. The others lie even farther, tens, hundreds, thousands of light years outward. We look at our star maps and imagine clusters. We imagine that the galaxy must be a crowded place. But astronomy is a trick of perspective. When you look at the band of the Milky Way in the night sky, you see a dense ribbon of sparkling light. But that brightness is not proximity, it is depth. You are staring through the thin disk of our galaxy, peering through a massive stack of stars all layered along your line of sight. If you could step outside and view the Milky Way from above, you would see them spread thin like scattered dust. The term nearest star becomes a linguistic trap. It makes the universe sound navigable, like a neighborhood waiting to be explored. It places a faint sense of hope in the minds of explorers and storytellers. If the nearest star is close, we only need to try hard enough to reach it. But space does not honor determination. It honors physics. It honors energy. It honors limits woven into reality itself. Each star is a locked island, separated from every other island by an ocean so wide that even the most advanced machines humanity has ever built barely escape the shoreline. When astronomers say Proxima Centauri is our closest star, they are not speaking to your intuition. They are speaking to mathematics. The numbers are precise. The implications are brutal. Nearest is a label we inherited from Earth, a world of roads and distances we can cross. In the universe, it simply means the smallest eternity. We do not measure star-to-star distance in kilometers. Those numbers fracture our ability to think. We use light years, distance multiplied by time, because only the fastest thing in existence can reveal how wide the gulf truly is. A kilometer is familiar. You can walk it, you can drive it. Nations measure borders with it. But between stars, kilometers multiply into meaningless strings of digits that stretch off the page. The human brain evolved to judge distances by footsteps, by travel time, by horizon lines we can physically reach. It never needed to imagine distances so large that even counting them becomes an act of futility. A single light year is roughly 9.5 trillion kilometers. Say the number slowly, and the mind softens it into a blur. 9 trillion. 500 billion. A numeric landscape so immense that comprehension evaporates. Light years solve that problem in the only way nature allows. Instead of asking how many kilometers exist between us and a star, we ask how long it takes light, the fastest phenomenon permitted by physics, to cross the void. Light does not accelerate or rest. It does not get tired. It races forward at 299,792 kilometers per second, every second, without pause. And still, it needs more than 4 years to reach Proxima Centauri. When you realize that, distance becomes less a measurement of space and more a measurement of cosmic time itself. Every star you see is a memory. The photons entering your eyes tonight were born long ago, somewhere far away. Some began their journey before you were born, some before the invention of writing, some when early humans were carving handprints into cave walls. Distant galaxies send us light that began traveling before Earth formed. You never see the universe as it is. You only see the universe as it was. Light offers truth, but with a delay we can never erase. Even the language of astronomy bends around this concept. Scientists speak of a galaxy 10 billion light-years away, yet they know the galaxy is not where it appears. While its light traveled, space expanded, stretching the distance like elastic pulled taut. The galaxy you observe is a ghost from the deep past. The real object lies far beyond the coordinates your telescope detects. Cosmic expansion drags every horizon outward, as if the universe is gently hiding its present state from us. When planning interstellar travel, this becomes more than poetic. It becomes practical. Distance is not only how far a ship must go, it is how long events unfold in its absence. Light that shows a planet orbiting Proxima today left years ago. A spacecraft launched tomorrow would aim for a target frozen in time. By the time it arrives, if it could, everything may have changed. Atmospheres stripped, orbits altered, worlds sterilized by radiation. Interstellar navigation is not a journey to a location, it is a journey into another era. So we measure with light years because they are the only units wide enough to hold the void. They remind us that between every star and every dream of reaching one lies a gap carved not just in space, but in time itself. Imagine building a spacecraft that never stops. It accelerates, hums softly, and glides forward for decades. Even then, the journey is not measured in days or months. It becomes a life sentence, crossing a distance that light itself needs more than 4 years to traverse. The problem begins with speed. On Earth, speed is freedom. Faster means shorter trips, wider horizons. A train halves the time of a horse. A jet shrinks continents into hours. But in deep space, speed stops being a tool and becomes a law. Nothing massive may reach light speed. If you try, the rules of physics tighten around you like a vice. Your ship gains energy, its mass effectively increases, and each additional fraction of acceleration costs exponentially more. You can lean on the throttle, but the universe pushes back. Even modest fractions of light speed demand brutal sacrifices. Suppose your craft could reach 10% of light speed, an unimaginable achievement by any standard we know. The journey to Proxima would still take more than 40 years, assuming perfect conditions, uninterrupted propulsion, and no attempt to slow down at the end. 40 years is not a trip. It is a generation. A crew launched in youth would arrive in middle age. They would celebrate birthdays in metal corridors, remember sunsets they will never see again, and grow older staring at a star that remains endlessly ahead of them like a mirage. And this is the optimistic scenario. Achieving 10% of light speed is not a matter of building a bigger engine. It is engineering on the scale of nations. Every gram of mass becomes a burden, every kilogram of shielding a penalty. If you want to travel faster, you must remove weight. That means stripping comfort, supplies, redundancy, and eventually, human presence itself. A ship with living people becomes a compromise long before it becomes a vehicle. Acceleration itself is not gentle. In space, you cannot floor the engine. Human bodies tolerate only small amounts of sustained force. A spacecraft must accelerate slowly, millimeters per second, so the crew does not suffer. At these rates, merely reaching cruising speed may take months or years, and when the midpoint of the trip arrives, the ship must reverse thrust and decelerate just as gently, like a runner slowly leaning back into the wind. You cannot slam on the brakes at a fraction of light speed unless you want to smear your vessel into vapor. The journey also drags through silence. There are no landmarks in interstellar space, no signposts, no horizons drifting past the window, just the occasional dust particle, weaker starlight, and a darkness so consistent it feels like a physical presence pressing against the hull. Every year becomes indistinguishable from the one before. At some point, the crew will measure time not by calendars, but by fuel reserves, maintenance logs, and the age of their own faces reflected in a mirror. So yes, you can launch a ship that never stops. You can aim it toward Proxima Centauri and let it glide like a silent arrow through the void. But the speed won't feel like movement. It will feel like waiting. The universe does not care how badly you wish to go faster. It offers only this: acceleration bounded by biology, energy bounded by technology, and decades stretched across an empty corridor you cannot rush through. Physics places a wall in front of every ambition. No ship with mass can reach the speed of light. The closer you get, the more energy you need. The universe resists acceleration, as if it is gently whispering. This isn't a poetic metaphor. It is baked into the structure of space-time itself. The speed of light is not just a number. It is the ultimate threshold. At low speeds, acceleration feels linear. Double the thrust, go twice as fast. But as you approach relativistic speeds, the math becomes cruel. Your mass, in a practical sense, increases. The ship that weighed a few tons on the launch pad begins to behave as if it weighs dozens, then hundreds, then thousands of times more. Every additional fraction of velocity requires exponentially larger amounts of energy. It is not that engines are too weak. It is that reality itself pushes back. Consider a spacecraft at half the speed of light. You might imagine it is halfway to breaking the cosmic limit, but half the speed does not require half the energy. It requires a mountain of fuel and engineering, pushing from 0, 5C, to 0. 6C demands vastly more thrust than reaching 0. By the time you aim for 0, 99C, the energy required becomes so extreme that no known technology, fusion, antimatter, even hypothetical drives, can provide it without turning the vessel into an energy weapon. Even if we had a perfect fuel source, there is another problem: waste heat. Engines do not convert energy perfectly. They generate heat, and at relativistic velocities, radiating that heat becomes nearly impossible. There is no atmosphere to carry it away. Space is a vacuum that traps thermal energy like a sealed bottle. The faster you move, the greater the heat load. Without colossal radiators, larger than the ship itself, the vessel slowly cooks. The physics of acceleration is always married to the physics of survival. Then comes time dilation. As velocity climbs, the crew experiences time differently. Clocks aboard the ship slow down relative to clocks back on Earth. To travelers, the journey becomes shorter. To those who remain, the ship is crawling. You could fly for years and return home to find decades gone. Children you knew have become elders. Your mission becomes a message sent forward in time, not just in distance. Relativity makes travel possible in theory, but it also isolates the traveler in a way that exceeds emotional imagination. Even communication becomes distorted. If you send light-speed signals to Earth while moving at a significant fraction of c, they stretch and weaken. The frequency lowers, the timing warps, and the gap between sending and receiving widens. Everything becomes delayed. Every response arrives after the world has changed again. Imagine begging for assistance and hearing the answer years too late. So when physicists say nothing can travel faster than light, they are not speaking philosophically, they are describing the limits of existence. The speed limit is not a fence you can crash through with enough stubbornness or clever technology. It is the geometry of the universe naming its terms. You may move through it, but you may never outrun it. The universe does not taunt you with unreachable stars. It simply reminds you, with unshakable patience, that ambition has a cost measured not in courage, but in energy, space, and time itself. Voyager 1 rushes through the void at over 17 kilometers per second. At that speed, it would reach Proxima in nearly 80,000 years. The probe will be long silent, Earth long changed, before it approaches a single alien sunrise. To a human standing on Earth, 17 kilometers per second sounds heroic. It is faster than any aircraft, faster than a rifle bullet, faster than any machine humanity has ever launched. It slipped the grip of the sun's gravity, crossed the boundary of our heliosphere, and now drifts through true interstellar space. Yet measured against the scales of our galaxy, Voyager is moving with the lethargic grace of a falling leaf. Its velocity is astonishing to the human brain and irrelevant to the cosmos. Imagine a calendar of civilizations. Empires rise, languages evolve, continents reshape their borders. Thousands of generations live and die. Somewhere in that distant future, long after every single person alive today is dust, Voyager would still be inching forward through the void. It is a reminder that space does not care how fast we feel we are going. Movement becomes meaningless when the destination is so far ahead that history changes more quickly than position. This is why our fastest spacecraft barely registers on the universal scale. They are engineered to traverse planetary distances, millions of kilometers, not trillions. They thrive in the solar system, where a year-long journey to Jupiter or Saturn is an achievement. But interstellar space is not the solar system stretched wider. It is a different category of existence. The distances multiply until speed becomes a cruel joke. All our ingenuity, all our rockets and ion drives and gravitational slingshots amount to movement so slow that time itself outpaces us. Even if we could launch something faster, the gains would feel shallow. Suppose we built a probe 10 times faster than Voyager. It would still take nearly 8,000 years to arrive at Proxima. 10 times faster again? 800 years. Every leap forward in propulsion buys you a fraction of the eternity ahead. Ship speed is not measured in human lifespan. It is measured in epochs. Generations aboard would live, grow old, and die without ever seeing the target grow meaningfully closer. And remember, Voyager is not burdened by humans. It does not require water, food, breathable air, radiation shielding, medical treatment, or psychological stability. A vessel designed for people would need mass, habitats, life support, storage, redundancy. That mass works against speed. Every kilogram slows the engine, drains the fuel, and pushes the launch cost toward the unimaginable. We are not fighting engineering limitations alone. We are fighting physics, biology, and the silent pressure of distance. The truth is sobering. Our fastest explorers are tiny messengers crawling across a cosmic highway that stretches longer than human civilization itself. They are symbols of curiosity, yes, but they are also warnings. If reaching Proxima Centauri requires 80,000 years of travel at our best speed, then space is telling us something gently but firmly. Not yet. Not with the tools we have, or the bodies we inhabit. Engineers dream of a ship traveling at 0. 1. C. The challenge is not imagination, it is energy. Pushing a modest spacecraft to that velocity would demand power rivaling entire nations, and stopping would cost just as much. At first glance, 10% of light speed seems reasonable. It is not relativistic. It avoids time dilation. It sits comfortably below the forbidden frontier where physics begins to twist. But the numbers tell a different story. To accelerate a vehicle of even a few tons to 0, 1c, you must impart unimaginable kinetic energy. Not energy measured in gasoline, or batteries, or rocket fuel, but energy measured in fractions of a civilization's total output. Every kilogram aboard becomes a weight in the equation. Every tool, every panel, every ounce of shielding multiplies the difficulty. The ship becomes less a vehicle and more a physics experiment carried across the void. And the problem does not end once you reach cruising speed. The universe is not a racetrack with a finish line where you skid to a halt. To arrive at Proxima, you must decelerate with the same precision and energy you use to accelerate. You simply blast through the star system like a stray bullet, a brief visitor streaking past alien planets in the span of minutes. The idea of arriving at another world and not being able to stop is the kind of cosmic irony engineers quietly dread. Fuel is the next betrayal. Carrying propellant to accelerate and then the propellant to decelerate doubles the load. But propellant itself has mass, so you must bring more fuel to move the fuel, then more fuel to move that excess fuel. The exponential spiral, known as the rocket equation, tightens its grip until your ship becomes mostly tank and almost no payload. Even a theoretical fusion engine, far more powerful than anything we've built, barely dents the problem. You can design it on paper. You cannot launch it in reality. Suppose you avoid carrying fuel at all. Suppose you tether your propulsion to Earth, a laser array the size of a city pushing a reflective sail thousands of kilometers wide. The sail is thin, nearly weightless. The ship is light, perhaps only a few kilograms. The beam accelerates it relentlessly until it reaches 0, 1c, or even beyond. This solves the problem of thrust, but creates another. Fragile payloads, zero shielding, and no way to turn around. A probe racing through deep space becomes a speck moving through a sandstorm. At those speeds, a grain of dust becomes a bomb. Then there is time. At 0, 1c, Proxima Centauri is still a 40-year voyage, longer than most careers, longer than many lives. By the time your ship reaches its destination, the world that launched it will be different. Nations will have risen and fallen. Technology will evolve beyond the vessel that left Earth. This is the paradox of interstellar travel. The more ambitious the mission, the more likely humanity will invent something better while it is still in motion. So 1C is not a dream. We are the ones who underestimate the cost of crossing them. Chemical rockets are miracle machines for planets. They lift us through gravity's grip, but stretched across interstellar space, they are useless, like trying to swim across the Pacific while holding your breath. The reason is simple. Chemical fuel is weak. It works wonderfully when you only need to climb out of a gravity well or hop between nearby planets. You burn a tank of liquid hydrogen and oxygen. The exhaust blasts downward at a few kilometers per second, and the vehicle climbs into orbit. That is enough to carry satellites, telescopes, and astronauts. But that power does not scale the way we need it to. For interstellar travel, you are not climbing a hill, you are crossing a continent of void. The thrust-to-energy ratio collapses. The rocket equation becomes a punishment. The more fuel you carry, the heavier you become, and the more fuel you need to move the fuel itself. Even the most powerful launch vehicles humanity has ever built are laughable in the face of the stars. The Saturn V, the Titan that carried us to the moon, achieved a velocity of around 11 kilometers per second when leaving Earth. In orbit, it was barely crawling by galactic standards. The ship was a mountain of propellant wrapped around a sliver of payload. It worked because the moon is 384,000 kilometers away, not trillions. Its triumph was scale appropriate. Beyond the solar system, it becomes a candle trying to light a skyscraper. You could stack boosters end to end, engines of every design, tanks filled with liquid cryogens, and still the rocket equation would mock you. To reach even a tiny fraction of light speed using chemical propulsion, your spacecraft would need more fuel than exists on Earth. A rocket becomes a parody of itself, mostly tank, almost no spacecraft, barely any payload. And worst of all, space does not give you gas stations. There is no roadside infrastructure, no refilling depots in the darkness. Once the tank empties, you drift forever. Even nuclear options don't free us from this trap. Chemical rockets are intrinsically limited by chemistry itself, by the binding energy inside molecules. They can only release a few megajoules per kilogram. Accessing the galaxy requires millions of times more energy per unit mass. Fusion and antimatter flirt with that scale, but these are not engines we can bolt to launch pads. They exist in theories and experimental chambers, not on the launch manifests of space agencies. Chemical rockets are also fragile. The farther you go, the more microscopic dangers accumulate. Dust grains become weapons. Gas molecules strike like bullets. To survive those impacts at any meaningful speed, you need shielding, heavy, dense, unforgiving. But shielding adds mass. More mass requires more propellant. More propellant adds more mass still. The equation spirals upward until you realize that the first stage of your journey is spent burning fuel simply to carry fuel for the second stage. This is why the cosmos is quiet. Not because nobody wants to explore, but because rockets, our loudest, brightest inventions, were built for local errands. Off the surface, into orbit, maybe to the nearby planets. They were never meant to run marathon distances between stars. The same engines that conquer Earth's skies fail utterly when confronted with galactic space. Chemical propulsion is a triumph of engineering on our scale, and a dead end on the universe's. For years, nuclear pulse propulsion promised hope. Atomic fireballs detonated behind steel plates, pushing humanity to the stars. The engineering would have worked. Politics and fear killed it before the first test. The idea was as bold as it was unsettling. Instead of carrying fuel in tanks, you would carry bombs. Each detonation would expand into a miniature sun, slamming against a massive pusher plate on the back of the spacecraft. Shock absorbers would soften the blow and convert the violent impulse into steady acceleration. Instead of a gradual burn, the ship would leap forward in a controlled series of nuclear kicks. It sounded insane, yet the physics was shockingly favorable. Where chemical rockets could barely push a ship to escape velocity, a nuclear pulse drive could, at least on paper, accelerate a vessel to several % of light speed. Suddenly the stars did not feel metaphorical. They felt reachable. The project had a name: Orion. Engineers at the height of the Cold War drew up diagrams of spacecraft the size of apartment buildings. Some designs would have dwarfed the Saturn V. They imagined crews living in rotating habitats, greenhouses for food, thick radiation shielding, and engines built to endure thousands of nuclear detonations. The vessel would not be sleek or elegant, it would be brutal. A moving fortress with a metal disc at the back, a blunt shape like something torn from mythology. It was the first real attempt to make interstellar journeys more than fiction. But promise has always been easier to imagine than to implement. Nuclear propulsion came with problems that were not technical, but human. Governments worried about detonating bombs in Earth's atmosphere. Test explosions would scatter radioactive fallout across continents. International treaties began tightening around nuclear weapons. Launching a spacecraft powered by dozens or hundreds of atomic devices became not an engineering argument, but a geopolitical nightmare. To proceed meant normalizing nuclear detonations as a form of transportation. No committee on Earth would sign their name under that. Even if the political climate were different, safety remained a silent assassin. A misfire, a damaged device, or an accidental detonation could destroy the ship instantly. That concern grows heavier when you consider a crew on board. The shields needed to protect them from radiation would add mass, and every extra ton demands more pulses, more bombs, more risk. The dream began to collapse under logistics. Not because the physics was wrong, but because the world outside the equations was unstable. Then came public perception. People already feared nuclear power plants and mushroom clouds. They feared invisible contamination, fallout maps, and cancers passed through generations. Asking society to embrace nuclear explosions as propulsion was asking it to abandon the fragile optimism it clung to after 2 global wars. The idea did not fade because it failed the tests of math. It faded because no one wanted to be the first to ignite it. Orion remains a symbol, not a vehicle. A reminder that we once had a path to the stars that was brutal, inelegant, and terrifying, but possible. Had history bent a few degrees differently, the first interstellar craft humanity built may not have been sleek and futuristic. It may have been a hardened ark riding shockwaves through the void, lit by the pulse of atomic fire. Antimatter engines exist in equations and laboratories, where single particles annihilate. In space, we would need grams, maybe kilograms. Producing that much antimatter would take centuries of global energy output. Antimatter feels like science fiction because it behaves like a miracle. When matter and antimatter meet, they do not burn or explode, they vanish. Their mass becomes pure energy according to Einstein's most famous equation. A single gram of antimatter reacting with a single gram of matter releases more energy than a hydrogen bomb. Engineers look at that number and see possibilities. The smallest fuel load imaginable powering the greatest journey in history. The idea feels intoxicating, until you look closely at the bill nature demands. On Earth, antimatter is not mined or harvested. It is manufactured, particle by particle, inside particle accelerators. We create a few nanograms a year, often at enormous cost. Trillions of collisions, thousands of megawatt-hours of electricity, all to trap atoms for fractions of a second before they decay or collide. We do not handle antimatter the way we handle electricity or fuel. We nurse it. We coax it into existence like a nervous flame on a windy night. Scaling that process up is like asking humanity to bottle lightning at oceanic volumes. Production doesn't just increase linearly, it becomes an exponential drain on every power grid on the planet. Even if we solve the production issue, storage becomes the next impossibility. Antimatter cannot touch anything. Not a container wall, not a molecule of air, not a speck of dust. It destroys itself the moment it touches ordinary matter. The only way to store it is to suspend it in electromagnetic traps, levitating it in cages of pure force. Those traps require perfect stability and constant power. Lose electricity for a fraction of a second, and your storage chamber becomes an instant bomb. Every gram becomes a latent disaster waiting to be triggered by a malfunction, a cosmic ray, or a micrometeoroid. Engineers have proposed hybrid solutions, antimatter catalysts that spark fusion reactions, microgram quantities that trigger controlled pulses. But even those systems require incredible precision. You are not simply lighting an engine, you are balancing the most volatile substance in existence beside a human crew. Radiation shielding alone would add tons of mass. Extra mass means more energy, more antimatter, more risk. The loop tightens around itself until you realize you are building not a spacecraft, but a starship-shaped containment facility. Then there is the political reality. No nation wants to weaponize antimatter by accident. A shipment mishandled could level a city. A storage error could erase entire facilities. The line between propulsion and catastrophe becomes paper thin. Even if humanity reached a point where antimatter was producible, safe, and storable, international trust would break before cooperation could begin. Who gets to hold something more powerful than every nuclear arsenal combined? People often ask why we don't pursue antimatter drives with more urgency, why we hesitate. The answer is not that scientists are timid. It is that antimatter is the closest thing we have ever encountered to pure power. It is the universe reminding us of an old truth. Energy is never free. For every dream of interstellar travel, there is a price tag written in the language of physics. Antimatter promises us speed, endurance, and the stars themselves. But it also promises consequences so absolute that even imagining them makes us pause. Breakthrough Starshot offers a clever workaround. Don't carry fuel. Use $1 billion laser on Earth to push a paper-thin sail into interstellar darkness. A gram-sized probe could reach Proxima in 20 years, and then speed past it in minutes, unable to slow down. The idea sounds elegant because it flips the problem upside down. Instead of building an engine that accelerates a spacecraft for decades, you place the engine on Earth. You let photons do the work. Lasers do not weigh anything, and the vacuum of space offers no resistance. A sail the thickness of a butterfly wing can catch the pressure of light and ride it like a cosmic wind. The craft accelerates continuously as the beam pushes it, faster and faster, until it leaves the solar system like an arrow fired from a bow. For once, engineering appears to bend around the wall of fuel and mass. The ship doesn't carry propellant, it simply rides light itself. But as always, the universe includes small print. The sail must be enormous in diameter and impossibly fragile. A single tear could collapse it. A stray particle could puncture it. The material must reflect light with extreme efficiency, enduring multi-gigawatt laser bombardment without melting. Designing such a material is less like designing a spacecraft and more like inventing a new category of matter. The sail must balance weight, resiliency, reflectivity, and thermal response with atomic-level precision. Even then, it must survive years in deep space, absorbing impacts from dust and radiation while spinning at relativistic speeds. Then there is the destination problem. A probe traveling at 20% of light speed reaches Proxima in a human lifetime. But it cannot break. There is no second laser array waiting in that distant system to slow it down. The probe flies through the Proxima system like a bullet through fog, crossing the entire planetary zone in minutes, collecting data in bursts, then vanishing forever into the void. It becomes a tourist with no time to look around, no ability to linger, and no chance of returning. A one-way glance is all it gets. Supporters argue that even such a flyby would revolutionize our understanding. A handful of images of Proxima b, a few spectroscopic readings, maybe signs of atmosphere or magnetism, this would already exceed every telescope we have on Earth. But there is a quiet cost hidden beneath the optimism. To gather meaningful data at those speeds, the probe must perform flawlessly. Sensors must activate at exactly the right moment. Antennas must beam information back across 4 light years. A single malfunction, a single misalignment, and the mission becomes a grain of dust, disappearing into darkness, carrying answers that no one will ever receive. The infrastructure required to launch one such probe is staggering. Thousands of synchronized lasers must act in perfect unison, their beams converging on the sail with microscopic precision. Weather, atmospheric distortion, thermal fluctuations, each becomes a threat. To avoid these obstacles, some propose building the array in orbit or on the moon, turning entire landscapes into power plants aimed at the stars. This is not a project for a single laboratory. It is a megastructure, a collaboration measured in decades and trillions of dollars. And yet the allure remains. Laser sails promise a path that does not depend on fuel tanks or fusion reactors. They whisper that, perhaps, with enough ingenuity, humanity could send its first ambassadors to Proxima within our lifetimes. But even those whispers come with a condition. You may look, but you cannot stay. You may visit, but only in passing. You may reach another star, but only as a ghost slipping through its system at unimaginable speed, gone before anyone has time to say hello. At a fraction of light speed, dust becomes shrapnel. A grain of sand strikes the hull with explosive force. The faster you go, the more the interstellar medium becomes a weapon, eating through shielding atom by atom. We imagine space as a vacuum, empty, silent, safe. But interstellar space is not nothingness. It is filled with dust, grains, stray atoms, microscopic fragments shed from dying stars. At normal spacecraft speeds, these particles are harmless. They pass unnoticed, barely tugging on the hull. But at 10, 20, or 30% of light speed, each becomes a projectile. A single grain of dust carries the kinetic energy of artillery fire. A pebble becomes catastrophic. Suddenly, the void is not an absence of danger, it is danger itself distributed across billions of kilometers. Engineers often begin their calculations with a single micron-sized particle. At near relativistic velocities, that particle delivers a burst of energy comparable to a bullet. Not because it is heavy, but because kinetic energy scales with the square of velocity. Double the speed, quadruple the energy. Space dust becomes weaponized by motion alone. A spacecraft crossing interstellar space becomes the target in a firing range, with every direction filled with invisible ammunition. The faster you go, the more lethal the environment becomes, until speed itself is indistinguishable from hostility. And these impacts don't just dent metal, they vaporize it. Collisions at extreme velocity generate plasma jets that carve tunnels through shielding material. The shock spreads into internal systems, cracking structural supports and frying electronics. The crew, if any, would experience the strike not as a bang or jolt, but as a silent flash of heat and radiation. The ship doesn't wobble, it bleeds. Protective layers erode molecule by molecule, each hit removing atoms like sandpaper grinding away a sculpture. To survive, you would need shielding thicker than anything we've ever launched. Perhaps a reinforced bumper made of tungsten, perhaps a cloud of sacrificial dust expelled ahead of the craft to absorb impacts. But every gram of shielding adds mass. and every kilogram of mass demands more propulsion. You cannot armor a starship like a bunker without accepting that your fuel requirements will skyrocket. And remember, the faster you try to go, the more shielding you must add. The problem scales upward until the ship becomes a fortress pushed by an engine no civilization can build. Even the dust ahead is only half the threat. Hydrogen atoms, individual protons, wait in the dark. At cruising speeds, they strike like cosmic radiation bullets. They burrow into hulls. They embed within metal lattices. Over time, they turn the vessel brittle, filling it with microscopic weaknesses until one hit becomes the last hit. The ship doesn't explode dramatically. It fragments quietly, shredded from the inside. People sometimes imagine putting a magnetic field in front of the ship, deflecting particles like a shield. But at relativistic speeds, a field strong enough to do this would resemble a magnetosphere on the scale of a planet. The energy demand dwarfs the needs of the propulsion system itself. You are not just building a spacecraft, you are building a star-sized defense system on its nose. This is why interstellar travel feels like war, not against an enemy, but against physics. The universe does not throw asteroids at you. It throws dust, atoms, and particles, each accelerated by your ambition. Movement becomes punishment. Speed becomes weaponry. The stars are distant not because space is empty, but because the space in between is filled with tiny bullets, waiting patiently for anything bold enough to cross their path. Beyond the heliosphere, cosmic rays are constant. They don't just damage equipment, they tear DNA apart, molecule by molecule. For humans, the ship becomes a drifting cancer chamber. Inside the protective bubble of our solar system, the sun does more than warm planets, it shields them. The heliosphere pushes away a portion of high-energy cosmic radiation, scattering or slowing particles that stream toward us from supernovae and distant galaxies. Step outside that invisible boundary, and the background becomes lethal. The ship will drift into a shooting gallery of charged ions, gamma rays, and atomic shards accelerated to unimaginable energies. These particles do not politely glance off metal. They punch through it. They pass through flesh and bone as if neither exists. Radiation in deep space doesn't behave like sunlight or X-rays from an airport scanner. It arrives in bursts, streams, and storms. Every few minutes, another high-energy particle tears through a cell, breaking strands of DNA like scissors cutting thread. Repair mechanisms struggle, then fail. Errors accumulate. Cancer becomes probabilistic rather than avoidable. Even with shielding, some particles slide through gaps, ricochet inside the body, and damage tissues from the inside. The threat is quiet. No dramatic alarms, no sparks, no hull breach. Just gradual, irreversible decay. Engineers know the solutions in theory. A thick metal hull, water tanks surrounding sleeping quarters, or layers of hydrogen-rich polymers. But shielding is heavy. Every centimeter of protection adds mass and costs fuel. A ship designed to safeguard its crew becomes too heavy to accelerate. A ship designed to reach another star becomes deadly to live in. There is no compromise that feels humane. Even spacecraft meant only for exploration, not habitation, must withstand years of radiation that slowly chews through electronics and erodes insulation until sensors fail and computers flicker. Solar storms add another dimension. In the inner solar system, astronauts have warning systems. They hide in shielded compartments when the sun spits flares. Interstellar travelers have no such luxury. A proton storm from a distant flare might cross the void and strike without mercy. A crew asleep in cryogenic pods, children born aboard a generation ship, scientists performing maintenance. None can react. Space does not send a warning. It simply arrives. Even robots struggle. Microchips degrade under constant bombardment. Memory registers flip bits. Circuits corrupt. A guidance computer might drift from truth by the slightest fraction every few months, until one day its course correction is wrong by millions of kilometers. At interstellar speeds, that error is fatal. A probe that misses Proxima by a fraction will never correct itself. It will wander past the star forever, carrying answers no one will ever see. Some dream of magnetic shields or artificial magnetospheres, enveloping the ship in a bubble like Earth's. But the scale is monstrous. To bend cosmic rays away, a vessel would need energy comparable to the output of cities. It would have to maintain that shield continuously for years or decades. One failure, one outage, and the hull becomes transparent to death. Radiation is not an enemy you can outsmart. It is a property of the universe. The cosmos is filled with debris from ancient explosions, accelerated to brutal speeds by collapsing stars and spinning black holes. The empty space between stars is not empty at all. It is saturated with the consequences of cosmic violence, waiting patiently. Inside that environment, a human spacecraft is not a vessel of exploration. It is a slow experiment in biology, resilience, and decay. Life support sounds simple until you must recycle everything endlessly. Nothing can break down, nothing can wear out. In interstellar space, you are not raising plants, you are engineering ecosystems. On Earth, life is effortless because the planet does the work. The atmosphere supplies oxygen, the oceans regulate temperature, and millions of years of biological evolution have perfected feedback loops that keep ecosystems stable. A person can breathe freely, drink water from rainfall or rivers, and eat food grown in soil touched by sunlight. Every step of that system is supported by gravity, climate, microbes, wind, and photosynthesis, forces that operate invisibly and continuously. Remove those forces, and everything collapses to its true cost. Life becomes a logistics project, measured in kilograms and calories. A spacecraft bound for a star cannot stock enough supplies to last decades. Food rots, water runs out, oxygen tanks empty. The crew must live within a closed loop where every molecule cycles endlessly. Waste becomes fertilizer, breath becomes carbon for plants, urine becomes filtered drinking water. Every system must not only function, it must never fail. A cracked plastic tube in a greenhouse is not an inconvenience. It is a structural threat. A fungi outbreak in a hydroponic tray is not messy, it is potentially fatal. And then comes entropy. Machines degrade, filters clog, pumps seize, valves wear down atom by atom. A laboratory on Earth can afford downtime, maintenance, replacements. A starship cannot. Spare parts add mass, mass demands propulsion, propulsion demands energy. The crew must become mechanics, biologists, farmers, and doctors simultaneously, able to repair anything from a broken LED grow light to a malfunctioning filtration membrane. Those tasks cannot be postponed for later. Ecosystems operate on the timescale of hours. Oxygen must be present now. Water must be pure now. Food must grow continuously, not seasonally. Plants themselves betray expectations once removed from Earth. Roots behave differently without gravity. Water clings to leaves and drowns them. Nutrients stratify. Pollination becomes impossible without animals. Artificial lighting must mimic sunlight 24/7, precisely tuned to the wavelengths crops require. If the ship accelerates or rotates to simulate gravity, the grow chambers must be engineered to withstand constant shifts in orientation and pressure. A single harvested tomato is not evidence of success. Even microbial life becomes a variable. The bacteria that help digest food or break down waste can mutate under radiation exposure. Strains that are harmless on Earth may become invasive in isolated habitats. The same ecosystem that keeps you alive may try to kill you if it drifts off balance by a fraction. There is no natural predator waiting to correct it, only crew members constantly monitoring the invisible chemistry of their own biospheres. Some propose purely mechanical recycling systems, machines that split CO2, recombine hydrogen, generate oxygen, and synthesize food from chemical stock. But such systems are delicate. They require precise inputs and flawless calibration. They consume power relentlessly. They fail suddenly rather than gradually, and their failure is absolute. Unlike soil, machines do not recover. They do not evolve. They do not heal. This is why interstellar missions are not adventures. They are ecological experiments without a safety net. Every breath the crew takes is a calculation. Every sip of water is a closed equation. Every meal is evidence that the ship is still winning an endless war against entropy. Life among the stars is not simply surviving. It is maintaining the illusion that Earth's effortless systems can be imitated inside a box of metal drifting through the void. Even if a crew survives biologically, the mind becomes the weakest link. Generations born in metal corridors, no stars outside the windows, no horizon, no home to return to. The mission becomes identity. Human beings evolved under open skies. We are shaped by landscapes, forests, coasts, mountains, the shifting colors of dawn and dusk. We wake with sunlight and sleep with darkness. Our brains calibrate themselves with seasonal rhythms and environmental variety. A starship removes every one of those anchors. The environment never changes. Every corridor looks like every other corridor. Every day feels identical. The sun is gone, weather is gone, the endless, subtle signals that shape mood, memory, and meaning vanish. What remains is artificial. LED lamps, filtered air, recycled water, and the constant hum of machinery. At first, a crew may treat this as adventure, a shared purpose, a frontier. But time stretches. Motivation is not infinite. Even on Earth, isolation damages minds. Antarctic researchers, submarine crews, astronauts on the ISS, each suffers psychological strain despite having communication, scenery, and the promise of return. Now remove those comforts. Imagine staring at maintenance schedules as years blend together. Celebrations become rituals that no longer connect to culture, geography, or history. Birthdays lose their meaning when the sky that marked your first breath is 4 light years behind you. Then consider a generation ship. The original crew may have volunteered, but their children will not have chosen this life. They will grow up inside a structure they did not build, following rules written for a destination they will never see. Their identity becomes the mission because there is no alternative. They cannot run away, rebel, or move to another city. Their entire existence is a single decision made by people who died before they were born. Purpose becomes dictated, not discovered. Every social tension becomes amplified. Arguments do not fade into the background of wider society. There is no wider society. A disagreement between two people becomes a political event that may echo for decades. A leadership dispute can fracture a community that has nowhere else to go. Trauma becomes generational, inherited through stories and rituals. The ship environment does not dilute emotion, it concentrates it. Even relationships change shape. Marriage, friendship, parenthood, these evolve in response to the environment. On Earth, personal identity can shift freely. You can leave, reinvent yourself, or find new circles. There is no anonymity, no fresh start, no freedom to vanish into a crowd. The ship becomes a village that never grows larger and never changes its scenery. Some propose artificial solutions. VR landscapes, simulated day-night cycles, rotating habitats to mimic gravity. But simulations are echoes of something absent. The crew will know the sky is digital. They will know sunsets are programmed. The comfort offered by illusion will fade if the illusion is the only source of meaning. A lifetime of virtual mountains is still a lifetime without the smell of pine, the randomness of wind, or the warmth of real sunlight. Ultimately, psychology is not a technical obstacle. It is existential. Interstellar travel does not simply challenge our engineering. It challenges our nature. We are not built to live in sealed tubes drifting through infinite darkness. We are built to belong to places, oceans, planets, communities, anchored in landscapes. A starship offers none of that. Only intention, routine, and the knowledge that you are crossing a gulf so large that no one you left behind will live to see where you arrive. A ship slow enough for humans must be inhabited for centuries. Children growing up aboard it may choose not to continue the mission at all. The future of humanity becomes a vote in deep space. The idea of a generation ship comes from necessity. If you cannot reach the stars within a single lifetime, then the voyage must span multiple lifetimes. Instead of sprinting through the void, you drift steadily, like a convoy carrying civilization in miniature. The first crew departs, knowing they will never see the destination. Their children are born knowing their mission is not to arrive, but to maintain momentum. Their grandchildren inherit a vessel already in motion, pointed at a world they have never asked to pursue. What begins as a heroic launch becomes a family legacy and eventually a cultural burden. Humans do not function as passive cargo. We change, we argue, we rebel. A generation born on Earth shares history, story, and origin. A generation born in metal corridors inherits none of that context. They will never walk through snow, never swim in oceans, never sit beneath a tree. Their reference point for home is the hum of ventilation and the glow of artificial daylight. To them, the destination is not a dream. It is a rumor. Their grandparents told them it mattered, and their parents enforced that belief. But why should they accept it? They live in the only world they've ever known. The ship. That ship becomes a society. Rules emerge, then evolve. Education focuses on agriculture systems, maintenance routines, conflict resolution, psychological stability, radiation safety, waste recycling. Children might be taught the history of Earth like a myth. Stories of oceans, rain, and stars they cannot feel on their skin. The very concept of Earth could become abstract, a place that existed once but never mattered to them personally. Their reality is the hull. And that reality comes with democracy. Even dictatorships cannot control thought. Eventually, a generation will ask a question that terrifies mission planners. Why continue? They may decide to turn back, find a stable orbit, or simply remain adrift in the interstellar dark. They may refuse to pour their lives into a cause chosen by ancestors they never met. The ship is not a tool, it is their civilization. They owe nothing to a planet 4.24 light-years away. Perhaps the crew tries to prevent this with law. Contracts, binding oaths, genetic screening of volunteers. But children cannot agree to decisions made before their birth. They will reach adulthood and demand autonomy. Some will see Proxima as promise. Others will see it as punishment. The community fractures. Politics appears. Factions form. What began as exploration becomes governance. Electricity budgets, population control, disputes over resource allocation. Every conflict is amplified by the ship's size. There are no distant suburbs to disappear into, no alternate jobs, no neutral territory. Even if consensus survives, entropy of culture creeps in, stories mutate, purpose erodes, holidays become detached from meaning, symbols drift from original intention, the voyage length dilutes identity, until mission becomes legend, then folklore, then superstition. Somewhere in the middle of deep space, the descendants of pioneers may simply stop caring. The The paradox is brutal. The only way to send humans to Proxima is to create a society that does not owe loyalty to Earth. And once you create that society, you lose the ability to ensure its choices. In trying to reach another star, you may create a civilization that chooses a different future, one that will not be yours. Fiction freezes its travelers. Reality is crueler. We can cool cells, we can preserve embryos, but no technology exists to stop metabolism and restart it decades later without catastrophic damage. The dream is simple. Put astronauts to sleep, let the ship sail silently for decades, and wake them near Proxima Centauri. A human life compressed into a single inhale and exhale. The journey becomes effortless. No psychology problems, no generational politics, no boredom, just a long night's rest between stars. But when science confronts biology, the fantasy collapses. Life is not a switch that can be turned off. The body is a network of chemical reactions, constant and delicate. Shut it down incorrectly, and you don't get a sleeping passenger, you get a corpse. Cryonics laboratories advertise preservation, using liquid nitrogen to store bodies at -196 degrees Celsius. They promise that medicine in the distant future may resurrect what science cannot repair today. But their patients are not sleepers, they are dead. The freezing process ruptures cells as ice crystals form like microscopic knives. Membranes tear. Neural pathways, our identities, shatter. Even if future technology could thaw them, the original architecture of their minds would be irreversibly scrambled. Cryonics is not a bridge to tomorrow. It is hope wrapped in stainless steel tanks. Real science attempts a gentler approach, suspended animation. In laboratories, animals like rodents and insects have been coaxed into torpor-like states. Their organs idle, their heartbeat weakens, and they survive periods that would otherwise be lethal. But translating such techniques to humans is another universe of complexity. Our cells are larger, our systems more interdependent. Brain tissue starved of oxygen dies within minutes. A miscalculation of a fraction of a degree can spell permanent injury. Medical science does induce short-term hypothermia during surgery. Patients are cooled to protect organs while surgeons work on the heart or brain. But these procedures last hours, not decades. After the operation, blood must be warmed slowly, carefully, and the patient must be monitored constantly. Even then, complications are common: nerve damage, memory issues, weakened immune response. That level of fragility on a starship would be magnified 1,000-fold. There is no ICU in interstellar space, no hospital, no replacement equipment if a valve fails or a heater malfunctions. Then there is the simple challenge of time. Biological tissues degrade even at low temperatures. DNA accumulates breaks. Enzymatic pathways drift. Over decades, cells might simply unravel. A cryosleep capsule would need to counteract all that entropy continuously, maintain temperature, ward off cosmic radiation, prevent ice crystallization, stabilize proteins. It would be less a bed and more a life support laboratory operating non-stop for half a century. Every circuit must function. Every pump must endure. One failure transforms hibernation into mass casualty. Even if we solved the biological side, the ethical dimension rises. Who signs the consent? A person in cryosleep cannot change their mind. They cannot flee abuse. They cannot advocate if systems fail. They become cargo, living cargo, dependent on machines and administrators. The moment their consciousness pauses, autonomy dissolves. A cryogenic crew is not a crew at all. It is cargo with hopes attached. The irony is that cryosleep is meant to simplify interstellar travel. Instead, it multiplies every risk. It is a technology that promises comfort but demands perfection. perfection in biology, engineering, and morality. Reality whispers a harsher truth. A frozen human is not sleeping. They are gambling their identity against physics, time, and luck. And the universe rarely offers second chances. The star we dream of reaching is a flare dwarf, violent, unstable. Its light pulses with radiation strong enough to strip the atmospheres of planets. What waits there may not be a home but a warning. Proxima Centauri is often introduced as a neighbor, as if the universe chose a small, welcoming star to place beside our sun. But Proxima is nothing like our sun. It is a red dwarf, the smallest and most temperamental class of star in the galaxy. It burns slowly and dimly, but with sudden bursts of rage. Magnetic loops snap, plasma erupts, and radiation floods the surrounding space. These flares do not gently warm planets the way solar winds do here. They slam them. They cook their skies. They blast their surfaces with ultraviolet and X-ray energy strong enough to sterilize them down to the rock. On Earth, our sun's storms are softened by distance and our magnetic field. We feel them as auroras, green ribbons shimmering above the poles. Proxima's planets are not so fortunate. To receive enough light to be habitable, they must orbit extremely close, within a fraction of the distance between Earth and the Sun. That intimacy is brutal. Imagine living beside a campfire that occasionally explodes. The planets endure constant bombardment. Their atmospheres, if they formed at all, are continuously peeled away like layers of paint scorched by heat. Astronomers watching Proxima have seen flares increase its brightness by factors of 10. It is the equivalent of a dim room lamp suddenly becoming a welding torch, then dimming back to normal as if nothing happened. A world orbiting such a star is subjected to violent swings in radiation. The background environment is relentless, not a stable cradle for life, but a roulette wheel that constantly lands on danger. And then there is the question of magnetism. Planets need magnetic fields to deflect charged particles. Earth's iron core gives us a shield that bends cosmic rays and solar wind away from our atmosphere. Without it, our oceans would boil away. But planets locked tightly around red dwarfs may be tidally frozen, one side perpetually scorched by daylight, the other trapped in eternal night. That locking reduces rotation and can smother the dynamo effect that generates magnetic protection. Atmospheric gases then bleed into space, torn free molecule by molecule, until nothing remains but bare rock. Proxima b, the planet that sparked excitement, embodies this dilemma. It sits in the habitable zone, but that term only means water could exist there in theory. It does not guarantee oceans, air, or safety. The very conditions needed to keep the planet warm are the same conditions that expose it to the star's tantrums. We imagine lakes and skies. The reality may be a cracked desert blasted by radiation, its air long since stripped away. Even if there were pockets of refuge, subsurface oceans, shielded caverns, it raises another question. Is that the future humanity wants? A civilization living in tunnels, avoiding daylight, never seeing stars except through thick shielding? We do not dream of traveling 4 light-years to hide underground. We imagine Earth-like horizons, gentle sunsets, breathable skies. Proxima does not promise those things. It promises compromise. This is the irony of our ambitions. We spend decades fantasizing about reaching another star, only to discover that the closest one might be actively hostile. Not because nature is cruel, but because it is indifferent. The universe does not place habitable worlds where they are convenient for us. It places them where physics allows them to exist, and those places are often harsh, unforgiving, and utterly unlike the cradle we call home. The planet sits in the habitable zone, but habitability is not generosity. Tidal locking, atmospheric erosion, magnetic storms, it may be a world of frozen night and scorched day, not an oasis. When astronomers discovered Proxima b in 2016, the world erupted in speculation. the nearest exoplanet, roughly Earth-sized, orbiting within the zone where liquid water might exist. It was the first time humanity looked at the stars and saw something that felt reachable, not in centuries of imagination, but perhaps within the span of our descendants' lifetimes. Images were painted in the mind, oceans reflecting a red sun, skies tinged with ember-colored twilight, alien plants swaying in gentle winds. But the more we examine Proxima b with physics rather than dreams, the less it resembles a sanctuary, and the more it looks like a trap. The first betrayal is the orbit. Proxima b hugs its star at a distance closer than Mercury orbits the Sun. It does so because Proxima is faint. To receive enough warmth, the planet must sit in a gravitational vice. That proximity almost guarantees tidal locking. One hemisphere forever faces the star, roasting beneath perpetual daylight. The other lies in eternal darkness, colder than Antarctica's deepest winter. There is no sunrise or sunset, no seasons, only a razor-thin twilight band circling the globe where temperatures might hover near survivable. Life, if it could emerge, would be confined to that twilight ring, clinging to the edges of shadow like moss on the cracks of a cliff. But even that narrow refuge is fragile. To keep an atmosphere, a planet must withstand the constant assault of stellar winds. Earth's magnetic field does this effortlessly, bending charged particles away from the surface. Its tidal lock slows rotation, which in turn weakens potential dynamo effects in its core. A weak magnetic field means radiation hits the upper atmosphere without resistance. Molecules split, escape, evaporate into space. Over millions of years, the air thins until nothing remains but vacuum. The so-called habitable zone becomes a technicality. Water could exist there if the planet still had any. Even in the best-case scenario, if Proxima b held onto atmosphere, it would be battered by flares. Proxima Centauri throws tantrums frequently, spewing ultraviolet and X-ray storms dozens of times more intense than our suns. Instruments on Earth have seen the star brighten violently, then fade back into calm within minutes. A single event could scorch the daylight side, sterilizing microbes and stripping ozone. Without a thick protective layer, the surface becomes toxic. The very calm red glow that looks romantic on artist renderings may be the sign of a star that burns its children. Some imagine oceans beneath ice, hidden networks of water shielded from radiation. There could be liquid seas in the everlasting night, warmed by geothermal vents or tidal forces, much like Europa or Enceladus. But life hidden underground is not the oasis we dream of. It is survival in the margins, clinging to heat sources in the dark, never seeing the sky, never evolving continents or forests or breathable air. If Proxima b hosts biology, it may be microscopic, slow, and buried, not lush and inviting. Then there are winds. The day side of a tidally locked world heats constantly. The night side freezes constantly. That creates violent atmospheric circulation, global-scale storms that move heat in endless loops. Jet streams become monsters. Hurricanes never dissipate. They roam locked hemispheres, reforged every moment by the same imbalance. And yet, Proxima b looks beautiful in imagination. We want it to be Earth too. We want our closest neighbor to be welcoming. The term habitable zone tempts us into hope because it sounds human, comforting, attainable. It means only one thing: that sunlight falling on the planet has the right energy to keep water liquid under ideal conditions. It says nothing about the air, the storms, the fields, or the future. The universe doesn't promise safety. It gives us possibilities and leaves the consequences to physics. Proxima b is not a paradise waiting to be claimed. It is a reminder that habitability is not kindness. It is a line on a chart, nothing more. Between stars lies dust, stray atoms, and the faint whisper of hydrogen gas. At high speed, those particles hit like bullets. Space is not a vacuum, it is a battlefield. We often imagine the cosmos as pristine and hollow, a pure void where nothing interrupts the silence. But the emptiness of space is a trick of human scale. We compare it to the air around us, or the empty space between objects in a room. That analogy collapses once you stretch it across trillions of kilometers. Even a handful of atoms per cubic centimeter becomes a hazard when your ship is moving thousands of kilometers every second. The void is not empty because emptiness is relative. To a spacecraft traveling at a fraction of the speed of light, every stray particle becomes a collision event. The interstellar medium, the space between stars, is filled with relics of cosmic violence. Supernova remnants, ionized gas, carbon dust, microscopic shards of silicates, icy fragments, and molecular debris drifting since the dawn of the galaxy. So sparse that a cubic meter might contain fewer particles than the best vacuum we can produce in a laboratory. But the distances you must cross are so vast that sparse becomes infinite. A ship moving through light years encounters quadrillions of these fragments. Resistance is not occasional, it is perpetual. Each impact is a flash of energy. A hydrogen atom at relativistic velocity becomes a proton slamming into the hull with the force of cosmic radiation. Dust grains strike like high-caliber rounds. Anything larger, a pebble, a shard of metal, a stray meteor fragment, would be catastrophic. There's no warning, no streak of fire like in the movies, just instantaneous destruction. A probe the size of a coin impacts your hull at tens of thousands of kilometers per second, and the result is a jet of plasma tearing through decks like a laser. The faster you go, the more space turns hostile. Engineers sometimes propose sacrificial shields, a thick Whipple bumper, to absorb impacts. This works for satellites in low orbit. It even works for spacecraft in the outer solar system. But scaling it up means building starships with meters of protective mass at their bow. Extra shielding adds weight. Extra weight demands more propulsion. Every attempt to armor the vessel makes it slower, hungrier, more expensive, and still vulnerable to particles you cannot see. Another approach imagines plowing a path through space using a cloud of gas or dust expelled ahead of the ship. The idea is clever. Hit particles before they reach you. Vaporize them. Absorb their energy in a distributed way. But this method turns the starship into a system constantly shedding material, losing mass, altering balance, and generating its own hazards. The protective cloud itself becomes a fragmentation field, and if the ship must break decades later, it must reverse the process, or risk running into its own trail of microscopic debris. Even if the vessel avoided solid dust, the interstellar medium's gas is no friend. Hydrogen atoms at high velocities collide with hull materials and embed themselves. They cause atomic displacement, knocking atoms loose from metal lattices. Over time, the skin of the craft becomes brittle. Structural integrity decays not from one dramatic strike, but from the slow, relentless erosion of molecular bombardment. It's like radiation poisoning, affecting the entire body of the vessel from the moment it begins its flight. You cannot negotiate with interstellar space. Its dangers are not storms you can wait out or obstacles you can detour around. They are baked into physics, into the fact that movement turns dust into knives and atoms into bullets. The vacuum isn't empty. It is simply vast enough that danger hides in distribution, not density. Every meter crossed is a gamble. Every kilometer is a roll of the dice. And every light year is an accumulation of thousands of tiny impacts. Each one reminding you that the universe is not a highway. It is a minefield stretching endlessly between the stars. A ship must aim at a moving target. Stars orbit the galaxy, planets wobble, space-time flexes. Miss by a fraction in year 1, and by year 40, you are billions of kilometers off course. On Earth, navigation feels simple. You drive toward a city, and it stays where it is. You fly toward an airport, and the runway waits patiently. Even the moon sits in predictable motion. Its orbit is calculable, its timing precise. But the cosmos does not offer stationary destinations. Proxima Centauri is not sitting still, gently waiting for us to arrive. It is circling the galactic center, pulled by stellar neighbors, dragged by dark matter, influenced by tidal forces we do not fully understand. To reach it, a spacecraft must target where it will be, not where it is. And where it will be is a moving probability that shifts over decades. Think of launching a ship and aiming at a star that is drifting at tens of thousands of meters per second. Your vessel is doing the same. A tiny error in the first year becomes a disaster in the 5th. Every correction consumes fuel. Every correction must be gentle enough not to break passengers, but strong enough to adjust a trajectory that stretches across light years. The ship becomes a ballet of microscopic adjustments and relentless vigilance. Each signal from Earth arrives years late, too slow to provide real-time steering. If something drifts out of tolerance, the crew must diagnose it alone, trusting imperfect instruments and aging sensors. Space-time itself complicates the task. Gravity bends paths subtly, constantly. A starship coasting through interstellar space will not follow a straight line. It will arc along invisible curves shaped by the mass of stars, gas clouds, and unseen dark matter halos. Even rogue planets, wandering worlds without suns, become potential hazards, detectable only if the ship crosses their shadow. Navigating through this terrain is not like sailing a calm ocean. It is like paddling a canoe across a stormy sea blindfolded, with every wave delayed by years before you feel its crest. And then there is relativity. If your ship approaches even a modest fraction of light speed, clocks aboard will drift relative to clocks back home. The faster you travel, the slower you age. For people on Earth, decades pass. For you, perhaps less. Guidance updates become asynchronous. What Mission Control believes is, current data is already ancient by the time it reaches you. If the planet you target shifts its orbit, if the star enters a flare cycle, if gravitational models change, you receive the news at the speed of light. Too slow to prevent mistakes that happened years ago. Sensors degrade, too. Instruments exposed to cosmic radiation accumulate damage. Calibration drifts. What once measured stellar parallax with millimetric precision now reports noise. A small misreading on day 10 becomes a massive error on year 30. The ship must correct constantly, sipping fuel, maneuvering with thrusters, bleeding momentum to keep its aim true. Each course adjustment is a trade-off. Steer too much, and you waste propellant. Steer too little, and you miss the target forever. Even arriving poses its own paradox. Imagine reaching Proxima B's orbit after 40 years of travel. The planet will not be waiting politely in front of you. It rotates. It wobbles. It interacts with the star's violent winds. The ship must brake, circle, and intercept, while still traveling at a speed that would turn any collision into an extinction event. One misalignment, one miscalculated burn, and the vessel sails past into the abyss, moving too fast to ever turn around. Space is not a canvas with grid lines and markers. It is fluid, dynamic, crowded with forces that ignore intention. The journey to Proxima is not a straight shot. It is a decades-long dance through shifting gravity wells, evaporating predictions, and instruments that age faster than the models they rely on. To navigate across nothingness is to chase a moving target through a universe that never stops changing. Imagine waiting years for a message to reach Earth, then years more to receive a response. No dialogue, no guidance, only silence and hope. Communication is easy to take for granted. On Earth, a message sent to the other side of the world arrives in seconds. We argue, coordinate, brainstorm, and reassure in real time. Even astronauts on the International Space Station can converse fluidly with mission control, but cross the boundary of the solar system and the comforting illusion collapses. The speed of light becomes a bottleneck. Delay transforms conversation into archaeology. Messages become fossils from the past rather than tools for the present. If a spacecraft travels to Proxima Centauri, every exchange with Earth must cross 4.24 light-years. Even at perfect efficiency, even with flawless antennas, every hello takes more than 4 years to arrive. A simple confirmation, "We received your message," takes another 4. Human communication becomes a decade-long handshake. No discussion, no debate, no shared decision-making. Just monologues launched into the void with the hope that someone will answer someday. In practical terms, this is not communication. It is prayer. And that assumes everything goes perfectly. Space does not respect clean transmission pathways. Dust clouds scatter signals. Solar storms distort them. Electronic systems aboard the ship degrade. Antennas loosen, sensors drift, software fails. A tiny calibration error in year 5 may go unnoticed until year 20, when Earth receives incomprehensible data streams that cannot be decoded. The crew, waiting, may never know whether the silence is caused by physics, equipment, or the simple fact that no one is left to answer. Communication is not merely about receiving responses, it is about guidance. A mission launched in 2080 might receive updated scientific models in 2090, but those models reflect the universe as it was a decade ago. If a catastrophic event strikes the ship, a flare, an equipment failure, a disease outbreak, any plea for help will arrive 4 years too late. Earth may craft a solution, but their instructions arrive another 4 years later. By the time the answer reaches the crew may be dead. A mission planner on Earth can respond urgently, but urgency means nothing when time itself stretches into light-year increments. Even the nature of communication changes. Messages must be carefully packaged, redundantly encoded, and broadcast with extreme power. The ship must carry dishes or laser links tuned precisely to Earth. That equipment must survive decades of radiation and micrometeoroid impacts. Every message is a massive engineering effort, not a casual voicemail. The ship's communications array becomes a single point of failure, fragile, aging, irreplaceable. And then the emotional cost arrives. Silence is not empty. It becomes a mental weight. Crew members who were once supported by family and colleagues now speak to a planet that cannot speak back. Their children grow up sending letters into darkness, receiving answers from grandparents long dead. Mission updates resemble time capsules. Advice arrives from past versions of scientists who never learned about new problems. In a generation ship, communication becomes mythology. Messages from Earth become artifacts, relics of a world that feels more fictional with every passing year. Eventually, the question that matters most emerges. What if a decision must be made? Change course? Abort mission? Divert for safety? The crew must decide alone. Leadership evolves into autonomy not because of rebellion, but because physics makes democracy impossible. The ship becomes its own civilization, with no external oversight, no external wisdom, and no lifeline stronger than faith. Interstellar communication is not a tether. Each message is a flare launched into darkness, with the sender knowing they may never see the answer. In that silence, the truth becomes painfully clear. Once a ship leaves our solar system, it is no longer part of humanity's conversation. It becomes its own voice in the universe, isolated, distant, and irrevocably alone. Once you reach Proxima, you cannot come back. The energy required to accelerate homeward is the same mountain you climbed in reverse. The crew does not explore, they emigrate. Space has no round-trip ticket. Hollywood teaches us to imagine voyages like road trips. You go somewhere, look around, and return home with stories. Real physics does not permit that luxury. To slow a starship traveling at interstellar speeds, you need as much energy as you use to accelerate it. And if you ever hope to reverse the journey, the burden doubles again. Every gram of fuel needed for braking must be carried from Earth. Every gram of fuel needed for the return must also be launched from Earth. The mass compounds like interest, spiraling upward until the ship becomes an absurd monument to fuel storage instead of a vessel for human life. Even the most advanced theoretical propulsion solves only half of the journey. A laser sail can accelerate you, but there is no mirror array waiting near Proxima to decelerate you. An antimatter engine might boost a craft into relativistic flight, but any return trip would require an equal volume of antimatter, meaning a quantity so vast and volatile that no civilization would risk storing it. Nuclear pulse propulsion could fling you outwards, but unless Proxima B is somehow stockpiled with nuclear devices, you will arrive with no way to slow down. It is a one-way dive. Those who dream of crewed missions must confront this truth sooner than they want to. Anyone we send will never come home. When the launch countdown reaches 0, the journey becomes destiny. A crew is not composed of tourists or explorers. They become emigrants. They leave Earth knowing their children will never see it. They will die there. They will build their lives around something alien, living in orbit or under a sky tinted red by a hostile sun. The psychology of such a mission twists expectations. We are a species anchored by roots. We go on vacations, we take flights, we explore, but we return. Return provides closure. It reminds us of who we are. Remove that element, and the mission becomes less about discovery and more about societal transplantation. The starship becomes a seed. The people aboard it are not scientists. They are founders, like colonists crossing oceans in wooden ships. Except the ocean is eternal, and the land they reach may not welcome them. And returning is not just difficult for people. Technology ages at different speeds. A ship launched today may take 50 years to reach Proxima. During that time, Earth will invent faster vessels. The original ship becomes obsolete before it arrives. If a return ship launched decades later ever crossed paths with it, it might overtake it effortlessly. Interstellar travel favors the patient observer, not the pioneer. Every outbound vessel risks becoming a historical artifact the moment it departs. Even communication suffers from this finality. You can transmit messages to Earth, but those messages arrive years late. Parents may speak to children on the home planet and never hear their voices as elders. Earth and Proxima become separate timelines, separate civilizations. The gulf between them is not merely space, it is irreversible divergence. So the question of interstellar travel is not how do we come back, it is should we go knowing we can't. They become exiles of their own choosing, carrying humanity's ambitions like a flame into a star system that does not care whether they survive. The universe does not promise a return journey. It offers only the path forward and the empty silence behind. A spacecraft launched today becomes obsolete before it arrives. A future generation might build one twice as fast, overtaking the original like a ghost passing through its wake. This idea isn't a thought experiment. It's called the infinite leap paradox. A probe leaves Earth in 2080, armed with the best propulsion system humanity has ever engineered. 40 years later, engineers invent a drive twice as efficient. They launch a second spacecraft, which accelerates faster, travels farther, and ultimately arrives at Proxima before the first. The pioneer vessel becomes a relic in motion, overtaken not by luck or sabotage, but by progress. The universe, which already resists travel, quietly adds humiliation, being beaten to your destination by those who never had to endure the journey. Technology doesn't evolve linearly. It leaps. Steam replaced sail, electricity replaced steam, transistors replaced vacuum tubes. A starship will depart Earth using today's best knowledge, unaware of tomorrow's breakthrough. The gap widens every year. The ship coasts silently in interstellar space as scientists back home invent fusion drives, laser sails, or antimatter engines. The people aboard may never learn that what once felt like the pinnacle of human achievement became obsolete before the stars outside their viewport even moved. This problem intensifies with time dilation. Suppose the ship travels at a fraction of light speed, fast enough for the crew to feel decades as only years. They live with the illusion of progress, believing they are racing boldly toward another sun, while Earth races past them technologically. In real time, humanity may solve propulsion, shielding, and navigation challenges. New ships might launch. They might pass the first ship calmly, efficiently, without stopping. The original passengers become a historical footnote drifting through darkness. And then comes the cruelest scenario. They arrive too late. If Proxima b ever hosts a human colony, the colonists will not be descendants of the pioneers. They'll be descendants of those who waited. The first ship, having sacrificed everything, time, identity, planet, arrives to find lights already glowing beneath alien skies, outposts already humming with life. They are visitors to a world they believed they were destined to found. History forgets them. Their journey becomes a tragedy, not a legacy. This paradox reshapes mission planning. Should humanity launch the first starship at all? Should we wait until propulsion is perfect? If we wait 50 years for a better engine, might we wait another 50 for an even better one? And another. Interstellar travel becomes a horizon that retreats as we chase it. We stall, not because we lack courage, but because we fear wasting centuries on something future generations will do effortlessly. In that hesitation, the stars remain distant. Some argue that exploration demands imperfection. The Polynesians who crossed the Pacific did not wait for satellites or weather forecasts. They sailed with courage, accepting risk. They did not postpone their journeys until better canoes arrived. But those voyages unfolded over thousands of kilometers, not trillions. No one on Earth would tell a family to board a vessel, knowing that a future ship would overtake them in mid-flight like a sports car passing a wagon. This tension between ambition and patience reveals an uncomfortable truth. Launch too soon and your ship becomes a museum piece adrift in the void. Wait too long, and humanity may never leave at all. The stars tempt us forward, but the future tempts us to wait. And somewhere between those impulses lies the reason why no one has ever left our solar system. The universe does not just challenge our science, it challenges our resolve, asking whether we truly want to go, or whether we only want to dream about going. Astronauts must leave more than home. They must leave Earth's oceans, its storms, its rain, its sunsets. Traveling to Proxima is not seeking freedom. It is abandoning every comfort life evolved to love. When we talk about interstellar travel, we focus on physics, fuel, and technology. But beneath those challenges lies something quieter and heavier, the emotional gravity that holds us to Earth. We are not minds plugged into machines. We are bodies shaped by millions of years of evolution. The colors of our sky, the pull of our tides, the smell of wet soil after rain. These are not trivial details. They are psychological anchors. They remind us we belong somewhere. They whisper safety. They whisper identity. Leaving Earth means cutting those threads, one by one, until the world we came from becomes a memory that ages like a dream. Consider the first weeks aboard a starship. You look through a porthole and see nothing but darkness. No clouds drifting lazily across the horizon. no birds circling in thermals, no trees bending in the wind. Space offers beauty in abstraction, nebulae, distant stars, the curve of the Milky Way. But that beauty is always far away. It is never tactile. You cannot touch it, hear it, or smell it. You are surrounded by sterile walls, recycled air, printed food, and artificial light. The human body adapts to these conditions, but the human spirit resists. We long for the unpredictable, the organic, the real. Earth is alive in a way nothing else is. Every sound carries meaning. Waves crashing, children laughing, thunder rolling across distant hills. In a starship, sound is mechanical. Fans, pumps, ventilation systems humming endlessly. The artificial hum is constant, unchanging. There is no rain tapping on windows, no wind whispering through forests, no thunder to remind you of the sky's power. The crew becomes surrounded not by nature, but by engineering. Astronauts aboard the ISS often describe an ache for Earth. They look down at continents and oceans glowing beneath them. They dream of grass underfoot and the taste of fresh fruit. And these astronauts orbit only 400 kilometers away. They know they will return. Space is temporary. That promise is their lifeline. Remove that promise, and the ache becomes something with teeth. Imagine the crew of a Proxima mission. They will never smell rain again. They will never feel ocean foam tickle their toes. They will never see dawn bleed into gold across a landscape of trees. Their children, born in transit, will never know what those sensations mean. Adults will try to explain sunsets the way we explain myths. They will show pictures. They will play recordings. But the children will not understand because they will never feel warmth on their face in the moment a star rises over a planet. They will live in a world with no horizon, a corridor, a ceiling, a destination they did not ask for. This emotional severing grows more intense over time. The mind starts to romanticize Earth. It becomes a postcard, a paradise that becomes more perfect with every passing year. Disputes on the ship amplify nostalgia. A broken air filter sparks arguments that end with someone whispering, "On Earth, this would be nothing." Resentment blooms. Memory becomes weapon. Homesickness becomes ideology. And in those moments, you understand something brutal. Interstellar travel is not simply an engineering challenge. It is an emotional exile. We are not just leaving a planet. We are leaving the one environment that shaped our nervous systems, our culture, our sense of beauty. We evolved to love sunsets, storms, oceans, mountains, seasons, wind. We evolved to breathe Earth. Everything beyond it is survival, not belonging. Traveling to Proxima is not a quest for freedom. It is the deliberate abandonment of the only world humanity has ever been built to adore. When you trace the equations, when you run the numbers, when you stare into the void with unblinking honesty, you find a truth that is both simple and ruthless. The stars are close in pictures, but the universe built walls of distance, energy, and time to keep them separate. The human mind is not built for scales like this. We compress the galaxy into charts and posters, pinning dots on black paper, forgetting they are separated by oceans of vacuum wider than history. We imagine space as an extension of exploration, just as our ancestors crossed mountains and seas. We tell ourselves that all frontiers yield to cleverness. But when you peel away hope, rhetoric, and science fiction, something colder emerges. The cosmos is not a puzzle to solve. It is an environment, and environments enforce their rules. Every attempt to reach Proxima Centauri collapses under the same constraints. Physics sets a ceiling on speed. Energy punishes acceleration. Radiation corrodes machinery and flesh alike. Dust grains morph into hypervelocity weapons. Navigation bends under relativity and gravitational drift. Even if we beat those obstacles, psychological collapse, generational chaos, and cultural erosion wait patiently on the other side. The universe does not hide these truths. They are open, mathematical, unambiguous. You can read them in textbooks. You can see them in every spacecraft that leaves Earth, crawling through space like a snail dragged across salt. When we dream of the stars, we imagine triumph. We picture landing on alien sands, raising flags, building domes beneath foreign skies. We imagine discovery, wonder, new civilizations, but the universe doesn't reward dreams. It rewards preparation, patience, and humility. No species, no engine, no myth can shorten it without paying a price so immense that it reshapes everything it touches. We are not denied because we are unworthy. We are slowed because reality has no interest in our wishes. The quiet answer is not dramatic. It doesn't roar like a black hole or flare like a dying sun. It whispers. It hides in equations. It waits in the cold. The cosmos tells us this. You may want to be everywhere, but you can only be somewhere. You may map the sky, but you cannot leap across it as if it were a lake. Stars are not destinations. They are islands separated by oceans so vast that even light, the fastest messenger in existence, moves between them like a tired swimmer. And yet, the answer is not despair. It is meaning. The fact that Proxima is unreachable today does not diminish us. It defines us. We live on a world that sustains us, supports us, embraces us with warmth and water and atmosphere. We have a sun that nurtures instead of seeks to destroy. We have air that feeds our lungs, seasons that mark our time, oceans that shape our dreams. The universe may be hostile, but Earth is generous, and our place within it is rare. When you truly listen, the cosmos isn't saying, stay away. It is saying, learn who you are before you try to become something else. They are in no hurry. The question is not whether humanity will reach Proxima one day. The question is whether we will be wise enough to understand the cost when we finally do. And so, as our journey through the impossible draws to a close, we return to the beginning. The dream of reaching Proxima Centauri is not naive. It is human. For thousands of years, we have looked to distant horizons and asked, what lies beyond? We built boats to cross oceans, wings to cross skies, rockets to touch the moon. Every great step forward began as a story, a whisper of ambition shared in quiet rooms. But interstellar space reminds us that some distances are not conquered by imagination alone. They require time, patience, and humility. We have seen that the path to another star is barricaded by physics, a speed limit carved into the fabric of reality, energy demands that dwarf nations, particles that transform into bullets, and radiation that gnaws at flesh and metal. We learned that human fragility is not just biological, but emotional, that a voyage lasting generations is not an expedition, it is the birth of an entirely new civilization, and that the star we reach may not be gentle, may not be habitable, may not care that we arrived. And yet, somehow, this truth should not discourage us. It should deepen our gratitude. Because the same universe that resists our steps gave us a planet that nurtures us. A world wrapped in atmosphere, bathed in sunlight, rich with water, forests, and life. A world where wind crosses valleys, waves crash on shores, and rain washes the dust from our streets. Earth is not merely where we started. It is a cosmic oasis, a gift in a universe of silence. So as you drift towards sleep, imagine the stars not as cold destinations, but as lanterns guiding us to treat our home with reverence. The universe is vast and ancient. It does not rush. It does not demand conquest. It asks only that we listen, learn, and look upward with respect. because one day, maybe centuries from now, we will reach Proxima. And when we do, the people who touch its soil will carry with them the memory of a blue planet that taught them how to breathe, how to dream. Rest well. You are part of an extraordinary universe.